Hello students, in the previous video we have seen what is phase space and what is phase trajectory. In this video we are going to see what is ensemble and ensemble average. So in the last lecture we have discussed about this example and how to draw the phase space trajectory in this phase space. So suppose at particular time we plot the point. So suppose this is the point. So at particular time instant, let's say t equal to t0, we have this phase space. So this means it explains all the system at that particular state, at that particular time. As the time progresses, this is going to change, and suppose now it becomes here, it becomes here, it becomes here, and it progresses on so on. And when you connect all these phase points, you will get the phase trajectory like this. Okay. So suppose there is one physical quantity f, and we have to take its time average, because as the time process the quantity can change. If you see macroscopically as a whole system, there is no change in the value, but macroscopically there can be some change, and therefore we have to take the time average using this. But for any system it is very difficult, because if you see this number of molecules are, if we consider for one mole, they are equal to Avogadro number, that is equal to 6 into 10 to the power 23 molecules. So this is huge, and this integration is very tedious task for a simple system also. So in 1902, Gibbs has discovered or he coined one term called as ensemble. Now, according to this ensemble, suppose this was the first case at t equal to some t0, then at t equal to t1, t equal to t2. All these points represent same system but at different times. The macroscopically there is no change in the system, but microscopically there can be change in the arrangement, because you can see, because they have some momentum, all the molecules, they are not stationary, they are moving with some momentum, and therefore there is some macroscopic change, there is change in arrangement of the system. So the collection of all such different states of a same system, of the identical system, is called as an ensemble. Now, if you see, this ensemble will contain the same system, only one is different states of single system. So therefore you can say that the energy of all states is same, because the microscopic properties are not going to change. And therefore in some books you also see that in definition, that ensemble is the collection of all states of equal energy but the identical system. This does not mean that there are two different systems identically and we are watching them at t equal to 0. But this is the same system, but we are watching it at different times. Therefore, the system is identical, but the microscopic arrangements are different, and therefore we can have a number of states, different states in a single ensemble. Now, why we introduce this ensemble concept? Because this calculation is very difficult, and therefore we introduce this concept. Now, instead of taking time integration, we just have to take the average of this ensemble. That we will call as an ensemble average. Now you can see here. So the number of phase points in this volume dq dt is equal to t. This is a notation. I am using the book S.K. Sinha. In that book, they are using this notation. Now the total number of phase points will be equal to the integration, and we are integrating by c. So this is nothing but total number of phase points or total number of states in the ensemble. Okay, they will be the same. Now we will define a distribution function, or we can also call it a probability density. So this is called as a probability density or distribution function. or more specifically statistical distribution function. So this is rho is equal to P upon C. So C is the segment integration of this P. So just like a probability, this is some fraction. Now this is the probability of finding a phase point at that particular state. Now in this given volume. So remember, this is, I'm talking volume, but it is in 6 dimensional. Now the total for a normal state, we know the integration of all probabilities must be equal to 1. And now in such case, we can define the macroscopic ensemble average of that particular physical quantity f is equal to this integration of f into this distribution function into this volume, and this is called as a ensemble average of some physical quantity. This is very useful quantity, and try to understand what is ensemble, because this is a very fundamental concept in the statistical mechanics. Again, I will explain what it is. It is the same system but at different macroscopic arrangements. So for example, let's consider a system. Suppose there are 2 states and we have 3 balls. Suppose initially we have this system. After some time, what we can observe this. After some other time, what we can observe is or we can also observe like this. Right? There can be n number of possibilities. So all here we have 2 states and 3 molecules. So we will get 4 different possibilities of their arrangements. Now these all states or these all arrangements come under a single ensemble. So this is the concept of ensemble. They cannot exist simultaneously, but they may exist, any one of them can exist equally. Now this concept of having any one of the arrangement in the ensemble is called as the principle of a priori probability. So priori probability. What it is? It says that finding this arrangement or this arrangement or this arrangement or this arrangement are equally probable. So suppose there are n number of arrangement possible, then each arrangement has probability of finding is equal to 1 upon n. So this is called as a priori probability. So if we check whether the system, so these two, the ensemble and a priori probability, are the fundamental concepts in the statistical mechanics. So there are different types of ensemble that we will see.